Hello everyone, this is Rebecca Arvin with the Water Environment Federation. I want to welcome each of you to the Fundamentals of Disinfection webcast jointly hosted by IUVA and WEF. Before we begin, I would like to quickly review a few logistics. All of the PDF PowerPoint presentations are available for downloading at WEF's FTP link. This link was distributed via email yesterday and will be distributed again tomorrow for anyone that registered after the time of distribution. The FTP link for this webcast also has information on how to receive professional development hours for those eligible to receive this credit. There are 2 PDH credits for this webcast. You will need to complete the evaluation form to receive the PDH certificate. Your feedback on this webcast is important and helps identify future webcast topics that are timely and helpful to you. Please follow the PDH instructions and check with your state accreditation agency on how to receive this credit. During this webcast, while you cannot speak directly to the presenters, you will, however, have an opportunity to submit questions by typing in your specific question via the question box that appears on your PC. Our moderator, Katie Bell, will be accumulating questions and direct them to the presenters at the end of this webcast. We will be recording the webcast. A link will be sent to all registered users tomorrow so that you can share it with other colleagues who could not attend the webcast. If you have any additional questions after the webcast has ended, please email webcast with an S at wef.org. Before we get started, I have a couple of poll questions. The first question is how many people are participating in the webcast today at your site? So let me just launch that. And if you could respond by site, I mean if you're participating in a group in a conference room, for example. If you're participating by yourself, just respond 1. Okay, it looks like we have the results. I'll go ahead and share that. Looks like we have a lot of people by themselves today. So I have another poll. Why are you attending this webcast? For educational reasons, a refresher, or for new information? And if you respond to other, if you could type in your question box what the reason is, that would be great. Okay, thank you so much. Looks like a lot of people getting credits today and for new information. So I just wanted to mention WEFCOM as well. I would like to encourage all of you to participate in a discussion on WEFCOM after the webcast in the webcast and online courses community. This is only available to WEF members, unfortunately. This is a little bit what it looks like. If you haven't been on WEFCOM yet, the discussions are in the left column. You can also join this community to keep updated on future webcast offerings. So our moderator today is Katie Bell. She's a principal engineer at CDM Smith in Tennessee. Thank you for being our moderator today, Katie.
Thank you, Rebecca. And also, again, I want to thank both WEF and IUVA for organizing this very timely webinar. And we do have a very interesting lineup of presentations today that will provide a broad overview of process fundamentals, regulatory considerations, and then some information on construction and operational experiences for UV disinfection for low-dose applications. And we are very fortunate today to have Gary Hunter here up first to provide some background on UV disinfection fundamentals and how these concepts apply to engineering design of UV facilities. Gary's actually a licensed professional engineer and senior, and I won't say how senior, but he's been around the block a couple times with UV disinfection projects, and he's at Black & Veatch in the Kansas City, Missouri office. He's responsible for the design, operation, maintenance, and troubleshooting of wastewater UV projects. And in addition to this work, Gary is quite active in professional organizations, and some of his notable volunteer efforts have included serving as the former chair of the WEF Disinfection Committee, as well as his current role as the secretary and board member of the International UV Association. So Gary, thank you very much for your time today and providing this background on UV and how we do it.
Thanks so much, Katie, and it's an honor to sort of be here and be a part of the group sharing thoughts on UV with folks today. This presentation is sort of an outgrowth of a couple of different presentations and workshops that have occurred. Last year at WEF our young professionals group presented a fundamentals of disinfection, and this kind of outgrows that, as well as in December there was another webinar on reuse applications using UV. So we're just kind of following a theme to kind of build on what others have already talked about. When we talk about sort of the basic level disinfection and application of UV, we have a lot of different terms that get kind of put out to different people at different times. The first term I want to review is transmittance. That is a water quality measurement that we can take with a spectrophotometer, but it's the amount of UV light that can be absorbed by the liquid. And it's typically a function of upstream unit processes as well as further upstream into what's coming from the rest of the wastewater collection system. So we can have impacts from industrial users off-site, which is upstream, as well as impacts from our different wastewater treatment processes. The second item is called collimated beam. This is a dose response for UV systems. Oftentimes this term gets confused with the fourth term, validation, but this is actually a test where one would go into the laboratory and expose samples to different doses of UV light, and which leads us to our next item, which is dose, which oftentimes is referred to as intensity of the UV light times detention time. Dose is sort of our critical parameter. It's analogous to essentially the system like chlorine, where we have dose. So those are kind of similar in terms, but it's really the amount of UV we're trying to apply and affect inactivation of the bacteria using either light and detention time. I did mention validation. This is an actual testing process that the UV equipment goes through that establishes, I won't say dose, but a design equation that then is used by both the designer and the operator to essentially run the UV system and design it. So validation becomes a very, very big part of this whole process in terms of the equipment. And then these last three are key elements that make up the UV system. The lamp that emits the UV light, and we'll talk a little bit about lamp technology and how it's applied. Oftentimes the lamps are enclosed in terms of UV sleeves. They don't necessarily have to, but it protects the lamp from water. And then we have the ballast of the transformer, essentially, that drives the ballast and allows us to generate the UV light. Once we move forward, essentially looking at effluent quality from whatever upstream process, there's a fair amount that we sort of have to gather information on prior to the design of a UV system. The first item is essentially transmittance. We talked a little bit about that term. I'm going to show some transmittance data on some of the projects that I have been involved with and how that goes up and down. The other item that we can actually look at is UV spectra, and we'll talk a little bit about that. Other item here is solids, and that would be the amount, usually in terms of milligrams per liter, coming from the effluent of the upstream process. In addition to that, it's very good to know the distribution, the size distribution, particle size distribution. So is it, well, I have 15 milligrams per liter, is that made up of very small particles or it's made up of big particles, because big particles are sometimes a little bit more challenging to disinfect than small particles. So it's nice to know where that is, because oftentimes the bacteria can hide within the solid. And then, the type of solid, is it a biological solid, is it a chemical solid, is it a mix of both? So kind of knowing that information helps kind of guide us down the path in terms of the UV. I'll put on here residual COD, or you could look at that as residual BOD, but that's the pass of the non-biodegradable fraction that is not removed through the treatment process. Oftentimes, this material might have a UV absorbing component to that, so we can have non-biodegradable UV absorbing material. Oftentimes, that comes from maybe an industrial source upstream that can impact the design and or water quality of the UV system. Color oftentimes has UV absorbers in it, and a lot of that is based on the different wavelengths of the color. Some colors absorb UV and some do not, so you have to kind of look into that. Iron, we'll talk a little bit about iron. Sometimes that can make some impacts. We have a slide on that. Hardness is one that we generally look at. That generally in terms of UV will impact or can impact operation and maintenance and cleaning frequency, so it's nice to know that up front. And then the bottom line is it's really key to understand and know what upstream process and what the flexibility of that unit process is. So if we're looking at UV, the take-home message is we ought to be taking data, and we need to be taking a fair amount of it just so we can drill in and better design and operate the UV system. So we need to know transmittance. So we talked a little bit about that. There are various compounds in the water that absorb UV light. We talked about iron. There are humic acids. So there's a lot of material within the water itself that will tend to absorb UV. And we refer to it as transmittance. Generally, when we measure it, it's actually absorbance. So we're looking at, we essentially convert absorbance to transmittance through a mathematical formula. Generally, when we measure it, it's looking at a different, we call it the UV light passing through 1 centimeter water. That's the definition. Just to recognize that there are other wavelength paths. 1 centimeter is generally the standard, but there are others that people use, so you need to kind of know that so you can measure it back to that point. And it's usually used using a spectrophotometer or sometimes what we call a single band photometer. So you can measure UV quite rapidly and the transmittance quite rapidly and gain an understanding of that parameter. This is data from secondary effluent UV transmittance that was online that we've taken. And notice we've tried to check it out through different time frames over time. And this is where we could look at, we've referred to red dye events and online events that we can look at. So the online data allows us to look at it. We could look at wet weather as well. We had red dye events. We had other things occur, and we can look at that very rapidly as time moves on to kind of match this up with actual collimated beam data to assess how well the plant's doing and how these different impacts would impact the performance of the system. So this is kind of gives you typical ranges. If we're trying to look at UV transmittance, we have the primary clarifier that can range from 25 to 50%, more generally on the 25. But you can recognize that really quickly secondary treated, whether that's through an activated sludge plant or trickling filter, those numbers can range quite rapidly. Usually the fixed film, the trickling filters are along the 50% range, and the activated sludge numbers can be as high as 80%. A lot of that is a function of the clarifier capacity. and the retention time in the clarifiers, how much additional settling we get. When we move to secondary filtration, recognize very quickly that it shows 60 to 80%, so sometimes even though we add filtration, we don't impact transmittance. What that would tend to mean is that we have some, again, non-biodegradable, soluble type of UV absorber in the water that's causing that to go down. You can see the MBR 70 to 55. RO can go up a little bit high. The key take-home message is what I mentioned a few minutes ago in terms of the mathematical formula. So if we know absorbance at the 254 nanometer, which is the wavelength at which we tend to get the best inactivation of the bacteria where things line up, you can essentially use that formula to absorbance values to transmittance. And this kind of slide shows that information. This peak here, the blue peak that you see, is the output of a low pressure lamp, and 85% of that is in that 254 range, and you can see that almost really matches up with the absorbance range of the E. coli. So that's really the key that we're trying to look at. This is a Hawk spectrophotometer. A number of those can do UV scans, and you can see the data down here where you can actually look at different wavelengths and where we're looking at. So if you get wavelength information in the 400, 500 range, that may mean that we need to be looking at trying to do some changes to upstream processes, because we're trying to target in and get the most bang for our buck in that 254 nanometer range. And this data was provided by Vic Moreland from the University of Hawaii on some of the research that he was doing looking at some impact of industrial users on treatment plants in Hawaii. With UV, we're trying to inactivate bacteria, so you can see that we start at some very large numbers in the, with raw wastewater and primary effluent in the 10 to the 7th to 10 to the 8th numbers, with total coliform and 10 to the 6th to 10 to the 7th and fecal coliform. You can see as we move through the treatment process, those numbers go down through secondary and through filtration and through nitrification and filtered nitrifiers. And some of that kind of holds the same, mainly because of the unit process and of what's in the discharging to the wastewater treatment plant. But after we know what's coming in, then we have to sort of target what's coming out. Most of this information is, contained in a discharge permit or an authorization to discharge. That might include fecal coliform and E. coli. Enterococci is one that we see creeping into permits. Many states also include total coliform as well, so you could see a number of factors there. A 30-day geometric mean for a fecal coliform might be around 200. The E. coli might be around 126, 30-day geometric mean. Enterococci somewhere around 33 to 35. So that kind of gives you a range. You can see that we need to get a fairly good removal of bacteria prior to the discharge to the receiving stream. I have here on the last one virus. Many states, by the way, they have in their preamble different sorts of requirements from a textural standpoint, not from a limit standpoint for virus. So that's something that one has to look at very carefully in how states will look at when we apply basic level disinfection. So then the next question is, once we know what the target organism is then how far do we need to go? Is that just a 30-day geometric mean? Does it include a 7-day geometric mean, so peak week type of thing? Does that include a peak day? And some states have even percentages, so they'll have a 30-day geometric mean with a percent of the time for a monthly value as well. So one needs to understand what the discharge requirements as they apply to various states and various permits. So when we go to size the UV equipment, there are a number of approaches that are used within the basic level disinfection arena. Some will apply the NWRI. We won't agree that that's good, bad, or indifferent, but some will do that. Some states use what we call PSS, or point source summation. It's still within their state code to use that particular number. So it's a mathematical model that looks at the intensity of the light and then tries to estimate the dose. The one that I want to kind of drill in is the one that IUVA is promoting, and that's generally a general secondary bioassay. Essentially, there's a process that's going forward looking at different organisms and applying either what they call a surrogate value. And so under NWRI, we use an MS2 phage as the surrogate. Under the general bioassay, we might use a different organism called the T1 or Q beta. Now, the whole key is what's in blue, is we want to try and use the right surrogate for the right application. So what we're trying to do with the surrogate is to essentially match that surrogate with what is needed for the compliance organism. So we want a surrogate that essentially has the same absorptive properties as the compliance, either E. coli or fecal coliform, because we can't get enough of that when we go through the validation testing. So this kind of gives you those two terms. The bioassay, you can see at the top, it's a laboratory test. Essentially, we can run lots of that information. We can collect that. It's relatively easy to essentially collect and assess that information over a period of time, even looking at various operational scenarios within treatment plants. Again, I showed the picture before at Transmittance. At key events, when that occurred, we ran collimated beam data to assess how well the system might respond. The other one, which we hear oftentimes, is validation. And that's where a very specific process is done to essentially validate the reactor, looking at flow, water quality, intensity, and essentially develops what is a performance equation that has, for lack of a better term, a envelope. So within a certain operating envelope, that equation is where it's been tested, therefore where it's valid. So equipment goes through validation. Generally, the equipment manufacturers perform that service to come up with the equation that then is used to size the full-scale UV system, and then you match that up with your bioassay data to come up with what your design dose should be. And actually, this is the collimated beam data from the previous transmittance data. So we ran different collimated beam data, so you can see there was red events and different times when different operating scenarios occurred. And we were looking at trying to determine where we might design based on this data statistically. We had wet weather events what dose we would need. And you can see even with a number of these items in terms of percent transmittance, even some very low ones, we could get, as we moved out to 60 dose and 40 dose, we were getting down under 100 most generally in terms of E. coli effluent concentration. So that gives us a pretty good confidence being able to collect that data over time and looking at different operational incidents at the treatment plant. Talked a little bit about iron. The key bullet here is the third bullet, looking at suspended iron to suspended solids ratio at less than 4%. So you can have all sorts of iron. Some iron has more impact than operationally, but iron tends to form some very small particles that can absorb UV, and if it gets more than about 4% in that ratio, you may not even achieve disinfection no matter what dose you have. So there's a lot that we can do with upstream unit processes. I talked a little bit about industrial users, removal across the primary, secondary treatment. Some even basic level have effluent filtration. There are a lot of different material that can impact that from industrial users like freeze-dried coffee or coating manufacturers. So real understanding, working with the industrial pretreatment program folks to look at what's coming in upstream as well as what is going on at the treatment plant. Just a quick review, the UV is made up essentially of three major parts: the UV lamp technology, the controls system, and then the process and monitoring. So all three of those systems need to work in tandem to have a successful UV system. If the power goes out, then we have challenges. If the control system goes out, we can have challenges. The lamps go out. So all three of these kind of have to work in tandem to make it work. There are a very large number of UV systems that exist. If I remember correctly, even as early as 1930, medium pressure systems were being used for disinfection. So it kind of moved a little bit. The low pressure in just after World War II, and then UV had input in the innovative and alternative grant funding. And you can see it's bookended here, pulsed power UV as well as LED, and I have some slides on that, which I'll talk about in a few minutes. So generally we see kind of two configurations. We see open channel, which is probably a very large percentage of what is used in terms of basic level disinfection. Lamps are suspended in the channel. They're easy to retrofit, easy to maintain and access, and enclosed reactors. Now, it should be kind of noted that enclosed reactors were actually the first application of UV for low-dose applications, and some of those systems got reactor during that, which provided some interesting challenges. But there are a wide range of flows and configurations that can be applied to enclosed reactors. There can be some challenges in maintaining and cleaning that equipment. In the past, most of those now have automatic cleaning systems, so it makes it a lot easier to use. This was sort of the workhorse for a number of years, the low-pressure systems. It came into the market in the 1970s. Generally, we're using a 65 to 85 watt UV lamp. Nowadays, it's really relatively smaller systems, ranging up to 3 MGD. We can use both vertical and horizontal configurations. Generally, the flow comes in and then goes out one end. The cleaning systems, and generally the flow paced. They work very well and have been very reliable. So the outcome, because the systems became very large, was to move towards the low-pressure, high-output systems, which emerged on the market in the 1990s. You can see that they're very, very large because it's based on wattage, so 165 watt and 1,000 watts. So there's a very large group of lamps that make up this sector of the UV market. Very large systems now into 370 to 400 MGD. They all have pretty much automated cleaning. Both some have just chemical, some have chemical and mechanical, some just have mechanical cleaning. But we get relatively long life, and the technology is moving 12 to 13,000 hours. The largest that we've seen, or longest, is around 20,000 hours. And there are a number of vendors that provide this type of equipment. Actually merged on early UV systems used the tube system. It had some challenges. Most of those challenges have been eliminated. You can see at the top of that picture is a smaller system. The flow essentially flows through tubes, and the UV lamps are located on the outside of the tubes, and then the UV moves in through the tubes into the UV system. It works relatively well. The bottom picture is a 30 MGD system located in Yakima, Washington. Washington. So another one of the movements is trying to look at what they call microwave UV. This system essentially has no filaments in it. They just excite the gas inside of it. That allows them to provide a good long warranty on the lamps. Notice the largest one is in Kingsport, Tennessee, but a lot of these systems going in, there's a system going in Texas as well. They hold that they don't really need a warm-up period, but they essentially use a magnetron, which is located, if you see the bottom picture in the white part, a magnetron that essentially excites the particles and forms the UV, microwave UV. Here's the medium pressure systems. These essentially moved into the market after the low pressure because systems started getting large. You can see the largest of this is 600 MGD. There are two sister plants in Birmingham, Alabama that have flows in excess of 600 MGD using the medium pressure technology. It works really well. It essentially has a little bit shorter lifespan on the lamps, but it allows us to squeeze a lot of disinfection into a very small area. We have newer things coming at moving to 800,000 watts and looking at vertical. The top picture is a Trojan Signa system, and the bottom picture is a Duron system from Wedeco. So there's a lot of movement, essentially as well as efficiency in terms of removal of the bacteria. This is kind of a newer system. At this point, it's more point of use looking, but where we see UV going potentially, maybe with different kind of applications of LED in terms of the wastewater. So there's a lot of things that we can essentially do with LED technology as it moves forward. So the theme of this graphic here is way we think and look at UV might not be the way we think and use it as we move into the future. And this is another one that has been looked at, the pulse power UV. A lot of work essentially looked at the Excimer lamps, the Electric Power Research Institute power. EPRI did a fair amount of work, both looking at this for wet weather as well as reuse. There were a couple of different systems. It does very good actually moving into the industrial side. A number of these pulse power systems are used on high purity systems in some industries, but it essentially uses a system that allows the wave to be pulsated like a heart defibrillator and uses the relatively high temperatures, several hundreds of degrees Kelvin. So in pulse, we may actually break cell walls and actually kill bacteria versus in most UV just inactivating them. And here are pictures of enclosed reactor systems. The top picture is a system in Georgia and a relatively large system in Georgia where they essentially get basic level disinfection. And then the bottom is a system in Melbourne, Australia, where they're trying to achieve UV disinfection. Enclosed reactor systems, if we have filtration, discharge requirements can be very successful, can be used, very simple to install and easy to maintain. As we look at UV and we look at the systems and we look at what made it up, there are a number of other things that have to be considered. Essentially the cleaning system, what's best for it, but usually we need some kind of overhead crane to access and allow maintenance to occur. We do have the control systems that can essentially look at intensity, you can look at flow, you can look at transmittance. So the control system essentially has to be tweaked to the system that is essentially installed. Hydraulics become a very big issue with UV systems, essentially trying to distribute the flow evenly across the different reactors that are used. Sometimes one can use automatic influent gates or maintain looking at the effluent gates to try and make sure. So that can be done with downward opening gates or automatic level control or weirs. So a lot of different, those are a function of head loss and sort of trying to fit the UV system within the hydraulic profile. Power becomes a very big issue, ensuring that we can maintain disinfection over a large period of time, and then whether or not we install it outside or inside a building. I just hit a couple of operational issues. Algae is one of my favorite ones, and trying to keep it clean. Algae will tend to collect on the UV system, and then trying to get on and like covers that might be used to control algae. No matter what happens, sampling is usually the key part of showing compliance. So the comment there is good sampling pays. It can be the source of issues and needs to be watched and looked at. That's where we form all of our data sets. So good sampling is one thing we need to watch out and take care of. And so the take-home message is that there's a lot of water quality parameters we need to look at in terms of UV. We need to know the bug, which one we're trying to understand, how they might apply to different sites. And there are other factors outside of just the UV system that need to be considered in terms of the selection and operation of the UV system. And with that, I'll turn it back to Katie.
Thanks, Gary. I think what we'll do is we'll hold the questions until the end, and what we'll do is go ahead and introduce our next speaker, and that's Paul Krause, who's a licensed engineer who was born and raised in Salt Lake City, Utah. And after he earned his engineering degrees, he went to work for the Utah Division of Water Quality in 1989, where he worked with the UPDES program, writing discharge permits. During this time, he was also involved with pretreatment, sludge, and stormwater issues. And then in 1992, he began working as the outreach coordinator for the division. And in this capacity, he was involved in providing technical and operational assistance to wastewater facilities throughout the state. Currently, Paul conducts process reviews for all the proposed wastewater facilities in the state. In addition to being a licensed engineer, he holds operator wastewater certifications in small lagoon systems, collections, treatment, biosolids, plant maintenance, and laboratory analysis. And I like this little trivia that Paul shared with us, and he's the 5-time winner of the Clean Lunch Plate Award at Hillview Elementary. Paul, thanks. I do want to tell you thank you very much for providing some regulatory perspective on implementation of UV. Certainly there's some chat for the understanding what regulations we need to meet.
Thank you. Hopefully everybody can hear this. Okay, what I want to talk about today is, if I've got screen control. First off, one of the questions probably a lot of people are going to ask is, what regulations do I need to meet? Now, depending on the area I'm actually in. So you're going to love the great classic regulator response will be, it depends. It depends on who you're dealing with, what state you're at. So I'm just going to use the United States as an example. I know we may have some people from other groups here, but in the 50 states, we have 50 variations of regulatory requirements for UV disinfection doing an operation. So what do I have to meet? What's my target? And it's a moving target. I'll be honest, a moving target right now. So in essence, it's a crapshoot. There's a comment in there about the Wild West, and we're going to actually talk about the Wild West because I'm out in the Wild West right now. And we're just talking about every state may or may not have different regulations, but there's some underlying guidance that they tend to follow. One of the things we're going to deal with is, first thing that you're probably going to want to deal with is what intensity, what type of intensity intensity does my facility need to hit? What do I do on something like that? And that's going to vary from, again, from state to state to state to state. What's my contact time? Am I getting ahead of the talk? That's what I'm worrying about. What's my contact time? How long is my contact time in there? What hydraulics do I have to deal with? Again, I need to keep the lamps always fully submerged on this. What type of redundancy do I have to have on this? Do I have full redundancy in that? Sorry, I'm having a little some tech. One of the big things any regulator is going to want to look at, some of the things they're going to be concerned with. They're going to want to know what the intensity is and obviously what the detention time is. So I guess it's the dose. Now they may think they're interchangeable. Again, dose may be expressed in microwatts per seconds or millijoules. And some vendors give you both information. And what's interesting on this, so again, with the regulatory all over the place, you may need to explain. Some rules some regulations may say it's in millijoules, and you have to make sure everybody knows the conversion on this. 1 millijoule equals 1,000 microwatts on this, because that's one of the things you have to deal with. Now, just looking at some of the regulatory requirements of dose, I'm just looking at some of the Wild West states around here. Colorado actually requires greater than 30 microjoules per centimeter squared. Idaho says nothing about it. I'm just doing an evaluation of the states surrounding me. Nevada, 30 millijoules. Utah doesn't speak to it in our regulations. Wyoming doesn't speak to it. So here we have some classic Wild West states in Gary's scenario, and only 2 of the 5 even have anything in their regulations dealing with that dose. So since that's all over the place, let's look at transmittance, regulatory requirements in that, and again, these 5 different states. UV transmittance. Again, it's the ratio exiting the water divided by the entering the water itself. The ratio, Gary already mentioned this before, it's the intensity, it's the light intensity in watts or centimeters squared. Entering, how much is transmitted through. I think this is kind of repetitive, but there's a good example of typically how you would do it, and a lot of people require, and that's a typical requirement on what's the transmittance through these things. What is your UV transmittance? So let's talk about Colorado. Says you need greater than 70% UV transmittance in your system. Idaho, again, doesn't speak to it. Nevada says 65%. Utah, we actually do have something in there. We require 50% on that. And Wyoming doesn't speak to it either. So at least if we had, when we talked about dose, we saw 30 was standard. So that you can see, again, the problem with dealing with something like that. Okay, disinfection concept is not new. The UV disinfection is not new at all on that. In fact, it's been around a long time. Gary mentioned about the 20s, but actually UV light was actually used in 1901 for disinfection in France for drinking water disinfection. Now, okay, so it's been around for 111 years. We might have a track record. Regulatory agencies might think we have enough data. Might. Again, the operative word there might be might on that. But there are some states that have no regulations in regard to UV disinfection. Some of it's really interesting. They don't have requirements for UV disinfection, but they talk about ozone. So that's a little bit behind the times, because some states haven't updated their design regulations in over 20 years. So again, I think everybody recognizes how much the technology has moved forward in the last 20 years, and the regulatory agency is, again, not catching up with it. So again, it's the typical glacial pace that some regulations move at. So typical regulations. So these requirements might be very subjective, and they might be subjective to whoever's reviewing your design that you're submitting, or even an upgrade or something like that. So it's going to be based on their preconceptions. A lot of times it's going to be based on it. So it's an educational process for everybody, I think, on this one. You need to take that in mind when you submit these things. So again, typically the classic problem is the technology explosion versus regulatory change. I think we all can agree and admit to that, where that typically is, because we know the pace of regulatory change is typically quite slow. So that's probably one of the messages I'm trying to convey to everybody is understand if you're designing one of these or coming in, you're being an educational opportunity for the review people. Okay, so what are we going to look at from a design standpoint? We're going to look at the design. We're going to talk about operations. I want to take a second and just speak to operations a little bit. One of the things that was mentioned being the bug. What type of bug are we going after? Well, and then what's interesting is typically we may be moving to E. coli. A lot of the states may be moving to E. coli. EPA is asking people to move to E. coli as a disinfection standard. Now, what's really interesting is from wastewater treatment plant, if you're operating a membrane bioreactor, that's easy. Probably your E. coli is not going to get through your membranes on that. So there was a debate that's gone back and forth on, well, if I meet my permit, do I have to disinfect on that? And how, at least we're dealing with a requirement to run your disinfection system all the time, regardless of really if you're making the E. coli number, because like I said, out of a membrane bioreactor, you will probably be making the E. coli number just by the barrier itself, but you know, the viruses and everything else is moving through. So there is a question, and some people are debating about our position would be yes, and quickly speaking to that too, there are some states where in the wintertime there is no disinfection requirement to discharge into their waters. So again, that's some of the operational issues. But again, I want to really focus most of the rest of the talk on design and design considerations, what we're going to deal with that. Again, what's really going to drive your operational aspect is whatever is in your NPDES permit or NPDES permit on that. We'll define that. And again, what you're maybe seeing now more and more, in addition to a numeric standard for to hit on your disinfection, you may also have a numeric or a narrative standard in the limits in the state. Again, what are we mainly talking about? Like Gary mentioned before, mostly we're talking about open channel systems. And two is a lot of preconceptions are based upon the experiences they had the mindset of the regulatory agency. A good example of that I know. So they had a pretty bad taste in their mouth on UV systems on that. And We tried it in a couple, and obviously that's really not a good idea. I can strongly recommend that for disinfection fine lagoon systems. So that was one of the things you ran into. But if they were like, oh, geez, UV kind of push back a little bit on that, but in this day we didn't have much problem with them, so we were more open to it. History on that too. So let's talk about some of the design regulations once you get there. If they don't have them in regulations and have written it, they probably are 4 major reference books that most regulatory agencies are going to fall back to. Well, these are the classic fallbacks. Metcalf and Eddy, which is a standard, probably most every review engineer or designer or regulatory agency has a copy of these floating around on that. 10 state standards. That's another one that a lot of people run back to, and particularly regulatory agencies use that, refer to that a lot. MOP 8, manual practice, another one, very good one to look at. On that. And like I said, membrane bioreactors and that, or we're going to reuse, moving to reuse, they may fall back to this one. So those are kind of give you a general idea of where the mindset may be from the regulatory fallback positions, or where at least where maybe some of these regulations came from as we're coming out of it. So I'm going to talk about each one of these a little bit. I wanted to talk about a couple of quick things out of Metcalf and Eddy. They talk about, they highly recommend pilot testing of all the systems. Well, we don't do much pilot testing in this state of our systems. We're going to accept that, but that's one of the standards. But you may see that requirement, and at least you know where that's kind of coming from. Again, whether they assume it's a plug flow reactor, not laminate flow, but a plug flow reactor design. So we'll speak to that. That's typically what we want to look at. We want continuous lamp submergence. I think everyone would hopefully agree that that's a good idea on a UV system. Particularly on that. So if you're going to be required that, but other states may. And again, where that may come from on that. Some of the other things I want to talk to is a simple first order reaction coefficient. Coliform at any given time is this the initial coliform concentration, exponential inactivation rate, and there's all those may or may not be published on which organism you're targeting, and then your dose. So you can back calculate what your effective dose should be. Well, that's actually maybe some of the basis of how you try to determine the dose and then work back to how much UV system you need to install at that point. But what I want to talk about is one of the things they speak to in there, and this is one of them may percolate into regulations. If you want a 2-log reduction and that, they're recommending anywhere from 30 to 60. So these are, you may see these numbers, and now you at least know where they came from. If you want a 3-log reduction, they're recommending between 60 and 80 millijoule dose, and 4-log reduction on that. Then the classic fallback, which is amazing how many states, more than 10, I can tell you that, use 10 state standards. And the best part is the first line in 10 state standards about UV disinfection is this: design standard, operational data, and experience are not well established. 1901. We're thinking it's probably a little bit longer, but that's one that goes in on the 10 states. That's the first opening paragraph in 10 states on UV. All they talk about is open channel design in UV and 10 state standards. And what their minimum requirements are 30 millijoules per centimeter squared. Hey, now we know where Nevada and Colorado got their number from. That's exactly, that was a fallback right to 10 state standards on that. Other thing they recommend is 65%. Utah's a little behind. Colorado's a little ahead on that. Nevada was right at 65%. But now you see where those two numbers come from, that 30 and 65 are coming out of 10 states. And the other thing 10 states recommends is total suspended solids less than 30 milligrams per liter. It's actually quite high on that. Some may speak to turbidity, some don't. 10 states, those are the three big ones that 10 states always establishes out there, puts out there. So you may see where, again, if you're dealing with your agency, whoever's reviewing the facility, from a regulatory standpoint, at least you know where the basis is. Now it's interesting, that was all open channel design. 10 states doesn't speak to closed channel systems at all. So again, that's on the discretion of whoever is doing that, apparently. And that, let's talk about MOP 8. Got to look at the Federation ones. So they have a little more expansive equation. They've expanded the first order reduction in that. And what we're talking about there now, we're talking about how fast the water is going to move through the UV chamber. That's one thing we're going to worry about. We're going to worry about how long it is. That's, again, going to be a function of time on this. And then we want to worry about dispersion through this. We don't want laminar flow going on this. We want some turbulence to be able to make sure there's some rolling or mixing going on in the chamber itself, so that particle doesn't have a chance to squeak by on the sidewall. On that, at least have a tendency to float and at least be carried closer to the lamps at that point. So that's one of the things we look at, what type of dispersion of that. And that's one thing that is of concern. What type of makes, and again, the light intensity of that. And then the suspended, the correction coefficient that, but it's total suspended solids. So they are taking into account the higher suspended solids, the less likely we have the effective disinfection. And again, Gary brought up a really good point early on about the dispersion or the characterization of the solids and the size of the solids itself. And I don't know anybody from a regulatory standpoint, and I may not be aware of everybody, that may be requiring that, but that's certainly something I would consider in design on that now. And let's talk about the reuse ones and that from National Water Research Institute. Again, National Water Research Institute, the book's out there. It has UV disinfection guidelines for drinking water and water reuse. The reason I brought this one up is this is the one we're now falling back on for anybody that comes in with a water reuse project with us on this. So what are they looking at? They're looking at what type of filtration you're running through and base the doses against that. So we're looking at, do you have media filtration, a rapid sand filter, a mixed media filter? Do you go to membrane filtration on that? And the last one, of course, would be reverse osmosis. So there's different levels, going to be different requirements for each type of filtration. Again, that's just going to be really a function of the suspended solids, the material that's carried in there on that. So again, some of the numbers we look at, the media filtration, greater than 100 millijoules per centimeter squared. That's a fairly high dose. Again, that would be typically with a sand filter or a mixed media filter on something like that. Fairly high dose. We were having, again, lively debates in the state about that very number on that. But again, what's interesting is they don't require a high transmittance. It seems to me that that's actually even a little less than goes back to the old 10 states number. But again, maybe with that higher dosage, it doesn't matter on this. But they also recommend an NTU of less than 2, which is kind of contradictory to the 55, but they are. That's one of the recommendations. So you may see that. And I'm sure none of you out there have ever seen contradictory regulations in your life on this. Some of the other things we want to look at. Now let's talk about when we go to a membrane. Go to a membrane. Again, if I'm just having to make an E. coli number from an operational standpoint, I could probably turn my UV off and make my number. From a regulatory agency, we don't want you to do that on that, so we're going to have that issue. So again, you get a little reduction in the dosage, obviously, because you're getting a little better water at that point. Again, not only looking at that type of transmittance, but now instead of 2 NTU, we're going to 0.2 NTU. So, and again, that's probably not an unrealistic number to have the membrane at all, but that's a fairly high dose. And again, mainly I think what we're trying to look for nowadays on something that's high dose is virus inactivation, because those are some of concern, at least to try to do something of that nature, go the right way. Okay, RO, again, now if I'm going through an RO membrane, you can imagine we're going to get a little less requirement on our dosage on something like that. So again, we've halved it. But again, I'm going through an RO membrane on that versus a mixed media filter down to 50 millijoules and now 90% UV transmittance on that, and an NTU of less of 0.2. Man, 90% transmittance should be quite easily achievable with an RO unit at that point. What are some of the other things we're going to worry about, though? We've talked a little bit about dose. We talked about some transmittance. What are some of the other things from a regulatory standpoint that are going to be of concern? Redundancy. Does that mean I have to have, if I have an open channel, do I need 2 open channels? Now, this is a debate that can go back and forth with the regulatory agencies on this. Do I need to have full redundant banks, or do I just need to have a full redundancy of both, or of the whole train, or a bank? Again, these are going to be negotiation points on this. Some it may not be spelled out, and again, the typical regulation will always say redundancy. Well, that's subject to debate on that point. Okay, typically, do we want complete redundancy? You know, except for a smaller application, yeah, maybe not. On that, again, that's the recommendation. A lot of people say, well, it has a complete redundant. No, if you have a 50 MGD facility, I don't know if you want to have that much redundancy in place. That's quite expensive to have. But these are the considerations you're going to get. Power supply. Power supply is key. If typically most plants have auxiliary standby power on that, one of the main things we require, at least from my standpoint again, is you have the ability to run the disinfection if you lose your power. A lot of plants don't have the ability to take the full plant load on the power supply, on the standby power, you know, and then typically you start to load shed if you lose power and your standby comes on, a lot of plants start to load shed. One of the things you can't really load shed is your UV disinfection at that point. That doesn't really fly. So and particularly on a retrofit, this may be a consideration, is do you have enough standby power to run the UV disinfection system on that if you have to run on standby power. Again, backup supply, you know, you need to, again, reiterate again, full load, and then when I'm talking about full load, I'm talking about full load of the disinfection system on that. That would be at a minimum that you would really, from a regulatory standpoint, that's one thing we would definitely be looking at. Some of the other requirements that you might see out there. Again, typical requirements, 30 millijoules per centimeter squared, and now you know where that number comes from. You know, I think Gary mentioned before the inactivation can be anywhere from 5 to 100. You know, you see the range all over the place on that. But as a floor, I would be willing to guess majority of the states would look at 30 as a minimum, again, falling back to 10 states. And then if you're going to a higher quality water or something of that nature, maybe even more. Another typical requirement you might see is 50%, probably 65 is more realistic on that. But at a minimum, you're going to have at least 50%. I would, again, looking at this slide and thinking about it, probably 65, probably again, the minimum standard is 10 states. But again, you have some contradictory manuals that say 50% is okay too on that. So these are, again, minimum floors on these. TSS, I think 30. I think it actually should be lower than that. That's personal opinion on that. But I think these are a minimum. If you're dealing with a facultative lagoon that discharges 100 TSS and as algae in the spring, you probably are not, UV disinfection is probably not your option at that point. That Gary already mentioned a little bit about the algae issues on that. So complete redundancy, again, what does that mean? Is it the banks? Is it the full channels? Is something that that's something you need to consider on this? And one of the other things you need to talk about is some type of backup generator, or at least to be able to handle the full load of UV disinfection at this point. And you need to take particular care, again, with lagoon systems or with trickling filters, again, because that 30 suspended solids you're probably not making, and you probably have, if you were putting it behind a trickling filter or a lagoon as a retrofit on something like that. I would imagine most agencies would ask for a little higher number for the dose to ensure effective kill, mainly due to the variability of the suspended solids coming off these things. Now, some of the things I mentioned, they're available, and they're available online. And, you know, Google is a wonderful thing on that. One of the things that's available online, you can go to 10statestandards.com and download the 10-state standards right there. If you haven't already, it's quite easy. It's a reference, and again, it's a baseline that a lot of states use for the basis of the regulatory requirements on that. And then another one is National Water Research Institute, USA.org, UV guidelines. You can download the whole UV guidelines, is available online too. So those are out there available to you at this point. With that, that really concludes the quick and very brief regulatory part of this talk.
Well, thanks so much, Paul. Before I turn it over, I can't help, but I'm going to step in here and interject just real quickly because there's several questions that have popped up on dose. I want to make sure that the doses that we've been talking about for these first two presentations today are actually tied to a bioassay surrogate organism, and usually the reference is MS2, and due to some pretty substantial changes in the UV industry, that's kind of in flux right now if that's the best dose. And Paul, I think you make a good point that that's why it's been a difficult thing to do from a regulatory standpoint to pin some of these doses down. But just as a reminder, when we talk about the reduction equivalent doses in those first two presentations, most of those numbers are tied to MS2 as a surrogate. So before we get into the questions a little bit more, I do want to give Dave Irwin an opportunity to talk to us about his system. He's been the wastewater plant manager since 1998 in Jefferson City, Missouri, and he's been operating wastewater plants for more than 30 years. He has a Class A wastewater operator's license, and he currently oversees the operation and maintenance of one of the world's largest continuously fed SBR treatment facilities. Dave's had an active role throughout the design, construction, and startup of the existing SBR facility, which was in the early 2000s. And in 2010, the Missouri WEA awarded the facility the Treatment Plan of the Year Award for the success in the treatment of the water, but also for the professionalism and knowledge of the treatment plant staff. More recently, Dave has shepherded the facility through the design, construction, and startup of a new UV disinfection system. And with some of this disinfection experience in hand, Dave has generously agreed to share some of the experiences through construction and operation of an open-channel UV disinfection system. Dave, thanks so much.
Thanks, Katie. I also want to thank WEF and IUVA for letting me speak today. I'm going to go through a presentation here on my experiences going through the design and equipment selection, construction, and startup an ultraviolet UV disinfection system here in Jefferson City. Jefferson City is the state capital of the state of Missouri. The treatment plant is located on the north bank of the Missouri River, directly across from the state capital. The original plant was started in 1969, had 2 primary clarifiers, 2 comminutors, and a gravity sludge thickener and an incinerator. In 1977, they added 2 more primary clarifiers, trickling filters, and secondary clarifiers were added along with coil filters. In 2003, we started up a new continuous feed SBR plant, and the old plant was demolished. This is one of our co-workers' pets on the thing. I just thought I'd throw him in there. He doesn't get a lot of pubs, so we thought we'd throw a picture of him in there. This is a view of the plant from the state capitol, looking across the river. Our maintenance building is here. Our administration building is here. On the right side of the slide is the headworks building, the SBR plant, and over here to the right side of the slide is the UV disinfection system. We're between the river and the Jefferson City Airport. Our SBR has a design flow of 11 MGD and a peak flow of 60 MGD. Our permit limits are 30 for BOD and suspended solids, and we have an E. coli limit here That's 1,030 per 100 mils on a weekly average and 206 on a monthly average. And our current flow is about 8 mgd. When we started looking at alternatives for disinfection, we went through all of these and then some. Ordinarily, a lot of people probably wouldn't look at a wetlands, but we just happen to be down here in the middle of several thousand acres, especially to our east. And we own 250 acres of our own, a small farm down here, so it was an option we looked at. But as you can see by the cost involved in it, it was not a cost-effective option. We did not want to go chemical. I was very much opposed to any kind of chemical disinfection for reporting reasons, for dose reasons, and regulatory reasons, because something that may be okay today, we were worried about 5 or 10 years wouldn't be okay as far as the chemical dosage. So we chose ultraviolet light. We had 3 manufacturers that we basically looked at for our UV systems. We chose manufacturer B. We chose manufacturer B, which would happen to be Ozonia, for the very reason that their bulbs were a vertical system instead of a horizontal. We wanted to be able just to pull a single bulb out and change it when it was bad rather than having to pull an entire module, and this system let us do that. Some of the things we also looked at when we were just making a decision on what to do, part of it was lamp replacement. We don't have any experience, or very little experience at this point changing lamps because it's only been operating for a year, and we have not had to replace only just a couple of bulbs. Our bulbs are $175 a piece to replace, and the quart sleeves that the bulbs sit in are $75 a piece. Monitoring performance, of course, the regulatory people want you to, you have to do more testing, and there's for our lab, before we disinfected, of course, you weren't worried about E. coli testing, both in and out of the system, and now you are. Cleaning is another part of the system. It takes time. It takes manpower. The system has a self-cleaning mechanism, but that only does so much. We have twice a year. We take our systems out, dip them in a dip tank, which I'll show you later, and clean them with the citric acid, rinse them off, and then put them back in. Monitoring the UV dosage. We want to make sure that each system is up and running, make sure that the dosage is high enough to do the job, to kill the, to disinfect the water and make it work from there, so that has to be constantly monitored as well. And then flow rate and water level, especially in our system, is very critical. Because we are in a floodplain and because we do have a lot of I&I, our flow rate is very carefully monitored, and we can switch channels to make sure that we don't take the risk of flooding our UV bulbs. And lastly, and it's not on this, but ballast replacement. Again, we haven't had to do those yet, but the ballast are about $300 when you have to replace one. This is again a picture of our SVR from overhead. The UV system is over in the far right corner. This was during the construction, obviously, and concrete had been poured at this point. Flow comes out of our SVR to the west side and through the east side, running pipes, delivered into the UV system, then flows over to the high water lift station. Most of the time, water runs out of our facility by gravity, but when the Missouri River level gets to a certain point, it won't, and the water has to be pumped through the high water lift station. Again, this is a close-up view of it while the guys were still working on it. One of the big deals during the design process we looked at is we told our engineering firm, which was CDM, we said, look, we do not want to pump our water twice. When we were designing the original plant in 2000, we went to our local DNR, state of Missouri, and said, hey, what's the odds of disinfecting? And it's funny because I remember it vividly. They laughed and said, you'll never have to disinfect wastewater on the Missouri River. That's ridiculous. So no disinfection system was planned for. So when you have to pump water part of the time because of river levels, we did not want to have to pump water out of our UV system and into our high water pump station just to pump it again. This was a very tough design, very, very close to not being able to be done. But they did CDM was able to get that done, and it's working very successfully. Here you see the footings have already been poured. The white pipe you see to the bottom left corner of the slide and all the way around is an underground well system. We had to pump dry sand points down in the water because we are, again, close to the river, and keep groundwater pumped out while the construction was going on. Again, this is a slide that's starting to form the walls after the footings are poured around the steel. The two pipes in the bottom, you see in the bottom of this there, where we've got one guy's actually walking into the pipe. These are the two 54-inch pipes that deliver water from the SBRs into the UV system. This is a shot of the UV system after the walls are poured, but there's no equipment in it, and that's a 60-inch pipe, which will deliver the water from the UV system into our high water lift station. 90% of the time we operate on a gravity flow basis in and out of the plant. Sometimes the 10% of the time we have to pump due to high river level. Of course, we were fighting a deadline. We had to have this project done within a 1 calendar year to meet DNR restraints for us. And of course, during the project, we got one of the largest snowfalls in the history of Jefferson City. That kind of thing you just almost could count on. Here it shows, you know, snow was in the facility. The rebar was already tied. They had to come in after the snowfall and actually dig all the snow out and clean up the messes so they could restart and go again. This is a picture of the 60-inch pipe being laid in the ground. It took, again, from the UV structure to the high water lift station. Once all the outside walls on the structure were poured and intact and had cured in place, the structure was filled with water to 1 foot above normal operating level, and that was to make sure that none of the outside walls leaked. We had to pass a leak test, so much evaporation was allowed, and that's all calculated by people smarter than me that we hired to do this sort of thing, and that we did. We were fortunate enough to pass our leak test. Once the leak test was passed, piping were laid, we backfilled around the basic structure and started on the control building. This brown block building you see here is where the controls will be for the UV system. This is the dip tank that I mentioned earlier being installed. The rebar tied around it. This tank is filled with a citric acid solution, and we pull our modules out and dump them in the citric acid solution twice a year in order to clean all the deposits and scale off the quartz sleeves. This is a blower. Part of our cleaning system on our UV system happens to be air. This blower was installed, and air lines and seed laying to the right side of the slide will be installed and hooked onto the bulbs to use air to help clean the quartz sleeves. This is the partial flume as it was being delivered and getting ready to unload and set into the structure. After the bulbs flow goes through our bulbs, there's a partial flume that keeps track of the flow, which sends that information back to the control panel so that we either light more lamps or dim lamps or turn lamps off depending on what our flow is, or actually open a second channel if the flow gets too high. As the water comes in goes through the bulbs, goes through some weirs, and again, Paul talked about you got to keep these bulbs submerged, you got to keep them wet. When you have an SBR that batch discharges, that's a real concern. So we had to build weirs in behind, and after the weirs, water is discharged over the weirs, it goes through these turning vanes you see the guys are starting to install. This eliminates any dead corners, it eliminates algae growth in the corners, which also have been talked about, and moves the water, speeds it along over into our partial flume. Eliminates all the dead spots in the structure. Here's another picture of all the turning vanes are installed. The openings to the right of the slide, the rectangular holes you see are where the weir will be mounted. The effluent channel and weirs will be mounted in those holes, and that's the discharge from the bulbs coming to there. This is a weir channel in place. Again, because of the SBR and because of batch discharges, that weir sits there and it stays full of water all the time. But when the flow comes to the bulbs, water then runs over these weirs down to this floor, which is the collection area, and heads over again towards these towards the turning bank. This is the treated water going over the weirs. You obviously see the light, UV light is on. The water comes in, fills these troughs, and then runs over. Again, when the flow stops coming to the bulbs, these stop running over, and water is contained in the weirs. Plenty of water in order to keep the bulbs wet, and also because we want to keep some of our bulbs on at all times. Because of a batch discharge, you can't get bulbs lit in time, and we would, if we didn't have this system, we might discharge water that hadn't been disinfected. So in order that doesn't happen, our bulbs stay on all the time, as some of them do, so that the minute water flow hits it, the bulbs are already on, already disinfecting instantaneously, and then more bulbs will light as the flow increases. This is one of the two filters we have in here. These filters actually are clean the power. One of the things too you got to consider is your line power coming in and your generator. How much variance in current is there? If you're like us, even though our power company swears their power is constant, it's not. And so you want to make sure you have a good, clean source of power so that you don't burn ballast and bulbs up prematurely. Here is one of our ballast cabinets. Each one of those little black deals with a red clip is a ballast, and each bulb has a ballast. These ballasts, you do not need an electrician to replace these ballasts. They're just unplug, pull out, slide a new one in, plug the cord back in just a few minutes, and an operator can do this. These are the transformers that we put in for this system. Obviously, a UV system that's capable of 66 million gallons a day of peak flow takes a lot of power, and these are the transformers we use. Kind of a laugher here. These are all-weather outdoor transformers, and somebody decided to mount them in the building. The panel on the left you see the slide, this is our main control panel for our UV system. This obviously is still during the construction where the people are still in their wiring and putting the cabinets, but the cabinet is on and being tested. This is a close-up view of the panel. It's a touchscreen panel. The operators, if you have a password, you can operate. It tells you what bulbs, what section, what channels are open, gives you all the information you need to know about what UV system is running. As you can see here, there was a fault on one of the wipers that also sends that. This is tied directly into our plant SCADA system, so the alarm, if this happens, the alarm is called to either the plant or to the person carrying the pager 24 hours a day, 365 days a year. This is a shot of our contractors installing the electrical wire. Again, with this much of a bigger system, there's literally hundreds of thousands of feet, even maybe miles of wire in this system. This is a shot of the UV modules being unloaded, 2 of them out of the crates that are shipped in. Again, this is the vertical system, which is what we wanted in order to make it a lot easier for us to maintain this system. Here you guys are moving the system from the crates over to the UV facility. The contractor instructed all of his operators and maintenance workers there that it's the old, if you break them, you buy them. So they were very, very careful getting this done. Here is the first rack going into channel 1. They're being lowered down in place. Again, you can look there and you see the rectangular holes where the weirs are in behind them. The water is going to flow from the front of the slide through the bulbs and again into those weirs. Each channel is capable of handling 33 million gallons of water. This are all the modules that are in place in channel 1, waiting for the wiring and the air lines to be hooked up to them. The guys down there making some final measurements to make sure that everything is in place and as it's supposed to be. Once all the UV modules were in place, along with our blowers, the valves, gate valves running in and out of the place, all the equipment was down in the facility. The cover was put on. We wanted our system out of the weather. These things never break down on a sunshiny day. It's always cold or it's always raining at night. And this cover lets us get in and out of the weather. It also it's lit, well lit, so we can work at night if we have to come in and do something at night. Plus, there's an overhead crane that hasn't been installed at this point, but it runs on this system where they can pick the modules up, take them all the way out of the UV system load them in a truck if for some reason you have to do that. You can run them over. The dip tank is inside there. You pick them on the crane whirls around to the dip tank. So for maintenance, cleaning, repair, whatever, we have an overhead crane that allows us to move our modules from anywhere in that facility we choose to do so. This is a close-up look of the quart sleeves with the bulbs in them. Looking down from the channel, looking up towards it, again, you see that it's very simple. These sleeves just slide right down in the bulbs, can be taken out one at a time while the flow is going. Very simple process. This is looking down in the top of one of the UV modules. You grab the little white and yellow deals, you pull a wire, come up with the bulbs, come up with them, you grab the bulb, unplug one wire, take the bulb out, slide the new bulb in, plug it back in, set it down in there, you're ready to go. It's a very quick, very easy, just a couple of minutes in and out. The little black motor you see in the center of the box, that's the wiper motor. Each one of those quart sleeves has a plate. There's a plate around each one with a rubber wiper, and that wiper goes all the way down to the bottom and comes back up. It is set at periodical intervals, and everybody's will be different. I think we do ours once an hour. Maybe if your wastewater had a little more stuff in it that would cause it to build up on the bulbs, you'd have to do more, or algae was worse. But that's about, we do ours about once an hour, and we try to have it run. Sometimes we don't always get it. We prefer doing it while the flow because it actually helps rinse stuff on by. But sometimes if you're not, it doesn't work out that way. This is the modules closed. You can see the air lines that are hooked to it, again, for the cleaning. You can also see all the electrical plugs. Another great thing about this, there's no unwiring. There's nothing to unbolt or unscrew. It's just quick connect couples on the air lines, quick connect couple on the plugs. You run a bar through the latches, through the clamps along the top of the thing, pick up one module at a time or pick up all three for maintenance or cleaning. This was startup. The guy in the back down on the channel was a representative from Ozonia. These guys are some of the guys that work for me. We have a full-time electrician on staff here and a full-time controls guy. As you can tell, probably by this picture, some of these guys were really, really excited. They were getting this new system in and something else to take care of. This is a photo of Channel 2 in operation still. This was some of the pre-testing that we were doing. We manipulated our flow in our plant during startup to max flow each basin. We wanted to hit it with a full 33 million gallons to make sure that everything responded. We also actually went out of our way to run our suspended solids up. Ordinarily, our suspended solids and our BODs here over the course of this plant averaged 5 milligrams per liter per month. We ran it all the way up to 35 and even 40 at one point just to make sure that if something disastrous happened, we would still get disinfection that would meet our state permits, and we did get that done. Again, this is the other channel in operation. You can see there sets the modules, the flow goes through, back. Again, you see a picture of the weirs, turns and goes back to our lift station. This is our UV system in its completed form, minus the sod and fence work. We are very, very pleased how this came out. We're very pleased that we don't have to pump our UV water. It flows by gravity to our pump station, and it worked out very, very well for us. This is a picture of our system at night, standing on our SBR basin and looking out towards the system. And again, you can see this gives you a good shot of the overhead crane and all the lighting that was installed so that in order we could work on this system at night. And to the right of the slide, you see the building, and behind the building, you see two separate air conditioner units. Paul talked about redundancy. We have redundancy in bulbs. We do have our own backup generator specifically for this system, separate from the plant generator. And we also have redundant air conditioner units because of the heat generated through the transformers and the ballast and all the controls in this system. We have two separate air conditioner units. If one fails, the other one's set for 2 degrees higher and it comes on. Or if we happen to get a really, really hot day, which we do get temperatures over 100 in the state of Missouri, both units could run to keep the building at a very cool temperature. Again, another shot of the facility at night. All done, everything in. Here you get an idea. You can see we have a transmittance, a module that monitors our transmittance. in the back so that we can make sure that it's in the range. Right now we average about 75% of UV transmittance for our facility, and we're very, very pleased. And that is the conclusion of my portion of this talk.
Well, Dave, thanks. I think since you're wrapping up your presentation, I'm going to start at the bottom and work backwards since we had some questions on your presentation first. Does that sound reasonable?
That's fine with me.
All right. One of the questions that we had was, did you have any issues with the tags that the UV system produced in the SCADA system? I think there's some challenges on another example UV system, and I was wondering if you could speak to that.
As far as the tags on the equipment being able to talk to one another and know what's what?
Right, and it looks like it may have caused a data issue with their SCADA system.
Okay, we are very fortunate in the fact that we have an on-site guy ourselves that handles our stuff for us, and we are also very fortunate that we have a contract with a company that's only about 2 hours from here that do excellent work. When we were doing our testing, that's when we ran everything through there up front. We had to make some small adjustments. Actually, for us, what originally was supposed to be channel 1 ended up being channel 2 and vice versa. And we actually made our own labels, and we labeled every module, every ballast cabinet, everything we had, so that there would be no could get confused. But as far as the input-output stuff, very few problems with that. Just a little bit like you would expect when you're trying to shake out a new system. But we were very fortunate. Everything was like it was supposed to be.
Okay, and then I've got just a couple more questions. We had a question on what kind of safety precautions that your maintenance staff takes when they're replacing bulbs.
We wear gloves, we wear eye shields, complete face shields, not eye shield, face shields. We also have, when we're cleaning bulbs, we have a black rubber, best way you call it, a long apron that the guys wear so that they don't get any acid splattered on them. And I think that's pretty much it. One guy can do this by himself, but if we're going to go out there, we generally always try to have guys work in pairs. If we have some kind of catastrophe, that might be different, but mostly we have guys work in pairs.
Okay, and I'm wondering if the question, it didn't specify, but I'm wondering if it was with respect to the electrical connections. Does that, when you open the top to that module, does that automatically shut off the power?
Everybody that works here has a padlock that is their very own and a key that is their very own. No one else has any. And before these guys are going to open those, if you open the cabinet, the power will go off. There are safety switches in there that don't allow that go off. But we make guys go shut disconnects off, put the lockout, tag out, and go to the next. And we're very, very serious about that.
Okay, well, thanks. And then, so while we're talking about power to the UV system, I had a couple questions about operational expenses. And what do you know what your average cost per year is for operation of the system, and then also what your unit power costs are?
I think our unit, if I'm not mistaken, our power costs are I think we're at 7 cents a kilowatt hour. And I can't tell you because we only ran just the one season, and again, we only do the April through October, so we're not full-time, we're not just part season. I don't have a good handle on what the electrical costs are to that. And the other thing is that this past year for us in the state of Missouri, all of our costs were very skewed because we are in the middle of what is a record drought. And our flow has been as low as I have. I've been here 34 years, and this is some of the lowest flows we've ever had. So instead of we've got water leaving the system in spots apparently and so this would not be a typical year for us for electrical costs.
Okay. And then just a couple of more O&M questions. I think you mentioned that the price of the replacement lamp, but if you could repeat that, and then also had a question on what the turning vanes in the effluent tank were made of.
Okay. Our bulbs, when we bought our system, we bought a contract through Ozonia, and they've guaranteed to hold the prices for 10 years. And the bulbs are $175. And the quart sleeves, I think, are $75, and the ballast are $300 each. And the turning vanes are they are steel, and then they were coated with an epoxy paint.
All right. So I'm going to let you off the hook for a little while and ask Gary to put on his thinking cap. I had some more fundamental questions, and going back to the beginning, one of the questions was, how do you define intensity? And Gary, I'm going to add to that, not only how do you define it, but how do you measure it?
Defining intensity would be, let's see how I can define that. The intensity would be the energy essentially coming out of the lamp per. And you would measure that using a, there are intensity measurement devices as well as sensors that can measure the joules of light that are being emitted by the UV lamp. So it's I wouldn't say it's an easy thing to measure, but it's a very methodical thing that you can buy an instrument. You can measure it either on a collimated beam. There are methods of measuring that, as well as you can get calibrated sensors that will measure intensity as well.
Right. And kind of following on to some of these energy questions, somebody asked if there was an analysis of greenhouse gas emissions of UV versus chlorination, dechlorination. And Gary, I'm going to throw that your way. If you don't have an answer, I did look up what the units were and have a comparison if you don't have that in your pocket.
Well, I don't have a total comparison, Katie, but what we did look at a number of years ago relative to more, I'm going to go from a sustainability comparison. We did, I don't know if greenhouse gases were involved, but we looked at it from, what do we call it, the triple bottom line type analysis. We looked at that, comparing it to chlorine, and because what happens when you look at the literature, and then there's a lot of literature out there that doesn't favor essentially ultraviolet light very heavily. Anything that uses power it gets some negative values. What we did is we tried to compare all of the elements that would go in. For instance, if you move back upstream and you look at chlorine, a lot of chlorine is essentially generated electrochemically as well. Generally, it's when people look at analysis, they're not looking at it's the delivery of the chlorine, or looking at the amount of emissions coming from trucks or other transportation methods that deliver the chemical to the site. When we looked at it a number of years ago for a particular plant, and we accounted for a number of those items, I would say UV came out cost effective in terms of looking at those particular numbers and accounting for that. I don't have a particular item in terms of emission of greenhouse gas, but I've looked at it in terms of comparing that to other disinfection technologies, and it is comparable.
Yeah, and the numbers that I have in my pocket are roughly 5 kilowatts per million gallon. 5 to 10 kilowatts per million gallon is kind of what we look at for secondary effluent disinfection for compliance with recreational water quality standards. So that's the 126 E. coli or 200 coliforms. And if we compare that to looking at a chlorine dose of like 3 to 6 milligrams per liter, we know that it's about 2 kilowatts per pound of chlorine when you generate it from salt. And so you're looking at roughly a maybe a 10 times or 10-fold energy difference if you take into account, like you said, Gary, all the pieces of the electrolytic process and the transportation of the hypo to the site. So there's a pretty substantial efficiency by using UV instead of chlorination, dechlorination for disinfection of these low-dose applications.
I would offer, Katie, again, it's a bit more complicated than what we could discuss in 5 minutes. And when you start taking into account, because what we even did is look at the, I think in Canada they have some surcharges, and we applied that to our transportation factors as well. So we've been trying to look at it as well. So it's not a simple analysis in terms of looking at it.
No, but at the end of the day, I think that it's a great question to ask, because I think that UV has historically been looked at as sort of a high energy process, and when we kind of take a step back and look at it compared to the other alternatives, maybe it's not quite as bad as we perceived it to be. So I think that's a good point. And I got another question for you, Gary.
Okay.
How is the size distribution of TSS particles tested, and do you know what the cost of that is?
Well, this particle size distribution, there is a analytical device that one can purchase or obtain to gather that information. And there are, let's just say, there are multiple different types of units that are available. One can go online and look at it. The one we had been working with when we were doing work in Arizona at the 91st Avenue, the utility purchased that unit. I think at that time, which was a number of years ago, it cost them about $35,000, but they were investing it in money to be able to use it for other things. You could actually go in and physically, you could do particle counts in terms of sizes, which you could actually go in and physically look at it would microscope it up so you could look at the size of the particles. So it's a unit. You can buy it. If we're looking at UV, oftentimes the UV manufacturers will provide that analysis for free. Oftentimes on projects that we've worked on, we like to have a little bit more knowledge, because when one ships samples, a lot of times, depending on the size and type of particle, it can agglomerate. So what you measure at the site and after shipment can be, and oftentimes are, two different things. So generally when we do particle size analysis, we try to get it done locally, or other utilities and folks that can provide that and that have that analytical equipment to be able to do it.
Yeah, and I've got some costs just in my pocket to throw out there, Gary. If you can't get it done by one of the manufacturers, who are usually quite helpful in doing that, if you are looking at UV, the cost for the samples, depending on what method that you're using, usually run in the $250 to $400 range per sample, depending on the method, whether you're using just a simple counting or if you're using more detailed analysis that you get a count of the size range in each, or whether it's volumetric. So that's not a large cost to get a lot of information. And then there's also some good reference materials out there. The issue with TSS, the particle sizes where we start to have concerns about UV working, Gary, are 30 to 50 microns. So just throwing that out there. I don't remember hearing that number.
No, yeah. If we get up much above that one, above 50 micron, then there's something going on, and a lot of shielding occurring within the bacteria. And that's really what we're trying to identify, is where shielding can occur.
All right. So let's see. I've got lots of questions here. I'm trying to order these, but let's jump around a little bit. One of the questions was looking for some recommendation for disinfecting flows with higher solids concentration and lower transmittance. So this gets into the discussion we're just having on the particle counting, Gary. I'm going to throw that to you.
The question is, can it be done? The answer is yes. can it be effectively done? The answer is yes. A lot of times you need to know, where are those particles coming from. It does pose some more interesting challenges because oftentimes as solids goes up, transmittance can go down, and then ultimately dose has to go back up to make compensation for then achieving the disinfection requirements. I think we need to sort of focus on some of the comments that Paul made. If you go into the textbooks and the reference materials, they would tend to argue against not, disinfecting using UV for higher solids, but generally when we get to the higher solids, then we would be looking at, additional collimated beam testing, additional even maybe pilot testing to confirm the design requirements and how often those higher solids go. Because we can make it work, it just may not be a lot of times as, sometimes it may not, after we get all done, be as cost effective as what we thought going in.
Right, and I think that's a good lead into the next question. We talk about all the advances that we've had in UV technology over the recent years, and now we're seeing systems validated well below 35% UV transmittance. And so I've got a question from someone who's a regulatory process reviewer asking, well, what do we do? We get requests for UV doses less than the 30 based on MS2, and also for effluent UV transmittance is less than 65%. What's a regulator to do?
Does that
I'm going to
go
throw that to you, Paul.
Yeah, I know it was. I guess it all depends on how much risk you're willing to take as the regulator, but given the data, if they have the data, again, it goes back to Gary's point about having enough data to validate that, as opposed to somebody had a study somewhere that said, 20 and 50% was just fine. Is that applicable in all cases? I would really want to know the waste stream you were coming out of, and that's all. Again, this goes back to the classic case-by-case answer. Again, what was my first line? It depends. You like that from a regulatory standpoint. But I think the point, really valid point, was there is no hard cast-in concrete rule that regulators need to abide by at all times, at all places, and in any place. And if they do, then that's pretty inflexible, and I don't think it's reflective of where the industry's at this point. Again, but you may be bound completely by your regulatory requirements too, and then you have to apply for an exemption, and we've done that before in my state too.
Yeah, so I guess just sort of a philosophical follow-up question, and I think this is a really great question, Paul. I think you began to touch on it. But so if we're talking about looking at this 30 millijoule per centimeter squared MS2 dose, are regulators expecting that there's going to be substantial virus removal with that dose, or are we not really thinking through that?
I think you answered your own question with the second part of that. I don't think a lot of them have, to be honest, a lot of people open up, thou shall have 30 milligrams per liter, or mil squared opportunity maybe when you're dealing with that group. Now, are the regulations, most of the regulations well thought out and latest science? Of course not, because they can't stay up with the times. So, no, but again, you're right. That's where the basis it all came from, and since we've changed from that too, it becomes interesting. So, but like I said, it's a regular, and what's interesting is I have people in my group that think 100 is probably too little because they want to make sure they get everything. So.
Yeah, and I guess that's sort of takes us to one of the other questions on here, Paul, is, what's the regulatory appetite and as far as the surrogate organism for wastewater disinfection? And the question was specifically MS2 versus T1 for fecal organisms, but just to throw out there, we can think about a T1 dose of 2019 being roughly
that.
right.
So
I mean,
I mean, I don't have a good answer for that because, again, a lot of these regulatory requirements are very old, and of course, you know, the classic line would be, "That's the way we've always done it."
yeah, and I think too that, you know, there's another good question related to, we talk a lot. There's a question about California's dose being 100 millijoules per centimeter squared, and I think sometimes we as engineers will pick up design criteria like the NWRI guidelines because there's a lack or absence of other design guidance and criteria.
Exactly.
What we haven't done is looked at the foreword of that book and said, this design criteria is targeted at 5 log polio virus removal. And then you need to ask yourself the question whether or not that's relevant to your application, right? Yeah, so I mean, I think it's a regulatory challenge, so it's going to be interesting to see where the state folks head in the future with some of the new bioassay organisms being used more frequently. Okay, so I wanted to, oh, go ahead, Paul.
No, the only thing I said is, again, I keep going back to, I think you need the regulatory agencies, given the economy now, a lot of them with fairly new people. This webcast is a good example of where they can get some of this, but it is an educational process, and be gentle with us, I guess. That's what might be the last pitch.
Well, I'm going to back a little bit to the equipment, and let's see, I had a question on microwave UV installations in the U.S. Gary, I don't know if you have that number off the top of your head.
The last I saw, it was in the, moving in that, I want to say 20 to 30 installations.
So nearly 20, and then what are the demand system compared to medium pressure or low pressure?
And how can I put this in? The microwave UV system, with the systems that we have used and we've piloted in terms of microwave, so achieving the compliance target, microwave works really well. Where we have had challenges with microwave have been on the operational side and the maintenance side. And I know that they have been working very hard and very aggressively to address those operational and maintenance issues that have existed. And so the challenge with that particular technology is what you saw maybe even 2 years ago isn't what you're seeing on the marketplace today. So, if you're really interested in microwave, you've got to get the latest and greatest because it's a real evolving situation. Does that politically answer that question?
No, I think that's great. I think one of the questions might have been geared towards the lamp technology, and I think maybe the answer is because that lamp doesn't have an electrode, the point of failure that is in conventional lamps is not there. And so the lamp lives can be as long as 3 or 4 or 5 or 6 years. The challenge is that you're taking the electricity through a magnetron and then to the lamp, and so the efficiencies are not as high as the low pressure amalgam lamps, and they're more, that electrical conversion to germicidal output is more closely aligned with what you see in medium pressure systems. maybe that UV system, and how did you evaluate the proposals?
We actually took the time to go to different facilities that had systems like we were looking at from the different manufacturers that we were interested by. This. We went directly to Ozonia. We negotiated our own price, and we purchased it ourselves.
And then, was there a reason you went with the low pressure, high output system versus a medium pressure system?
That I'm trying to remember. I don't remember exactly how it came out, but it worked itself out. We all agreed that would be seemed to be what was going to be the best for us operationally here in Jeff City.
Yeah, so there was probably an interest in the longer lamp lives of the 12 to 13,000 hours compared to 8.
Correct, and even now, even when we started looking at this a couple of years ago, the bulbs now are better than they used to be, and there's a more variety of bulb suppliers than there ever used to be. There's what they call the off-market or black market bulbs, where you can buy bulbs cheaper.
Okay. There's a couple of questions here with respect to design standards and which organizations are leading the research and development of technology and application. And I do want to put a plug out there for the International UV Association. It's iuva.org. Website. I should get that information to Rebecca, and she can post that. And that is one of the organizations that is leading research of what's going on in the UV technology.
Had been replaced, blah, blah, and sent them right back down in the channel. The channel was empty, of course. We drained shut the gates, drained the channels down, cleaned them. Matter of fact, my guys went out to the power washer and made sure they got all the algae and any deposits off the walls, the gates, everything, and then set the bulbs right back down in the dry structure. They're sitting out there right now.
Okay. And then just while we're talking about seasonal disinfection, there was a question about what kind of redundancy you provided for a system where you are able to take that system out of service part of the year. Do you provide a full channel redundancy, or was it an extra bank, or what did you guys provide?
Plant won't even take but 60 peak, and we've never seen more than 45. So we felt fairly confident that we've got about almost a 20 mg leeway in the amount of bulbs we have. This flow is not necessarily going to be the same. You can be discharging more water depending on how many basins get discharging at the same time, more than water that's actually coming in. And so we feel pretty confident while we didn't put a separate system in for redundancy, we do have enough leeway that if we would look at 2 or 3 modules, we'd have plenty to go even if we had a rain event.
For you, Paul, what are the most stringent regulations that you've encountered during water disinfection? I'm assuming that's wastewater disinfection, in terms of transmittance intensity, etc. And then kind of as a follow-up, Arizona has best available technology limit of E. coli for 4 of 7 daily samples less than 2 mpn per 100 milliliters with a daily single sample max of 15. Is that reasonable treatment to be reached from a BNR treatment facility followed by sand filtration?
I think that's we're starting to talk almost Title 22 water at that point, aren't you?
Sounds like it, huh?
Yeah, that's the ones that jump to mind as being as stringent as any of them in California's requirements. I'm trying to remember, it's 2. Somebody help me out on this off the top of my head because we're not California.
It's 2 total coliforms.
Right.
And I can't remember if there's a daily maximum. Gary, are you working in California these days on the reuse side?
Yeah, there is a peak. I believe it's 23, Katie.
Okay.
Right. And I can't remember the transmittance off the top of my head, but again, that's probably from my limited knowledge, the Title 22 is about as stringent as a requirement as I've seen, and I have seen that put in behind activated sludge plants. Particularly, the question that was being asked in that was for a BNR plant, I guess, what's the ultimate disposal? I mean, if you're going to reuse, it makes sense, but I think you see a tendency to put reuse disinfection standards on discharges into surface water bodies, which I think may or may not be appropriate at that point, too. And I think that you need to always consider what you're discharging into. I don't know if that answers it really well or not, but again, does that
I think it is, and I actually had a question I'm going to tag on here too. You talked a lot about UVT, and actually I've seen UV transmittance as a permit requirement, and I think sometimes we get confused because UV transmittance is a water quality parameter that's a function of what you're doing upstream. So when you put that in a permit, is that, I guess, it's sort of like COD or CBOD or ammonia or something like that. How does that play into understanding the performance of the UV disinfection system?
Oh, I think it's one where the permit writer may have not had a full understanding what UVT meant, and that can very well be too on that. You're right. It's a water quality. I think. Number 2, I would think inlet on that. So they're trying to ensure that somebody just doesn't put it in and never change the bulbs. And not that we've ever seen that happen before, too. Or I've had some that have actually turned them off. Said, "Well, we couldn't. It was too expensive to run, so we just turned it off." Which has a tendency to not. You don't really tell your regulator that. From that standpoint. But yeah, I think that's what the understanding. And again, we have a requirement behind an MBR where we have a minimum transmittance, and we also they have to report the run times to ensure that they're always on.
Yeah, so that's
in a permit. That's in a permit.
Yeah. So one of the questions I got just as follow up was how frequently do you have to change the lamps? Is that driven by the permit or other?
That's typical. Well, it may be driven by the permit on just what's the minimum transmittance, and I think that's what it was trying to divide. But I think any good operator would. In fact, I would defer this to our friends in Missouri. You're going to change it as needed. But again, it's when somebody starts to write that into a permit. No, excuse me. When you write it into a permit, I think what you're looking at is somebody who's trying to micromanage it to when they can change the bulbs.
Yeah, and for sure, I mean, we see that actually out in California where operators have actually had to change out lamp the 12,000 hours because that's what the validation of the system was based on. So even though the intending question to sort of look how that's handled from a regulatory standpoint in different states.
Oh, it's all over again, it goes back to it's a crapshoot.
All right. And Gary, I've got one more really good one for you. Somebody asked, if a system's validated, can you use somebody else's bulbs as long as they are equal in the specifications? This is, so if you buy a system from X manufacturer can you get lamps from Y source?
Really the bottom line answer to that is really you shouldn't. With that lamp and that technology, and will it work? The answer is yes. If you're trying to achieve validation, you've invalidated the system because you've used the different. It's a challenge. I'll put it that way. But the bottom line is, if you're not following what the validation says, then really the system doesn't have validation.
And that was Gary, that's a great answer. Thank you for putting it in that context. Okay, Dave, I've got one more question for you, I think. On your system that you have installed, is that dose varied based on water quality or the UV transmittance, or is it just flow pace?
We have a combination of flow pace and transmittance. We monitor both.
And so that's automatically changed, or is that manually?
It's automatically. All that information is fed into the computer, and it automatically lights or dims or calls for extra bulbs, or even if the flow pacing is not only run the UV system but also runs the gates. If our flow gets high enough where we need the second channel on, it starts lighting lamps and starts raising gates and so forth. But we have in that one slide I showed back where we have transmittance meters that monitor continually and feed that information into the controls.
So I think that gets the answer. Gary, I've got just a couple questions in here that you may be able to help us out with. One is, in general, how many lamps are required per unit volume of? Oh,
we're 5 minutes over our time.
I'm sorry, I didn't even catch that. We are over. I think we're down to the nitty-gritty questions. So if there's follow-up, send those to Rebecca, and we can try and get some answers back out if there's some burning unanswered questions. If you are interested in hearing more about UV, please join us at the Disinfection and Public Health Conference in Indianapolis at the end of February. There's more information on WEF.org, and again, joining us for the IUVA WEF Fundamentals of Disinfection, UV Disinfection webinar.